All right, so what we just saw was that if you like the Boltzmann entropy, or at least the logarithm of the statistical weight of such macrostate in a gas of non-interacting particles in which I have assumed that the particles are identical but distinguishable, is given by this expression. Okay, and the only assumption here is that, okay, the total number of particles is large, but also the individual cell occupations is large enough to justify the use of Stirling's formula. So just remember that's what we did. Now what we would like to do is to find which is the set of occupations that maximizes this object. Okay, in analogy with Clausius' theorem. Okay, so what we are going to say is, okay, imagine for a moment that this entropy of Boltzmann is really equal to the true thermodynamic entropy. Then it would be interesting to look at what happens when you isolate your system. Okay, so its energy remains constant because there is thermal insulation on it, and then you find what's the maximum entropy. Is that state a state that is compatible with what we know about the ideal gas in equilibrium? We will have to see. Okay. So first things first, we are going to then use as our parameters in our optimization these cell occupations. We are going to play with them around to see what specific distribution of occupations is going to maximize the statistical weight. But of course we cannot change them completely at random or completely freely. We are constrained because we know that the total number of particles is given. Okay, so we cannot have any we cannot make any arbitrary changes individually in the cell occupations. We always must ensure that the sum equals n, and because I just said that for Clausius, for the principle of maximum entropy to be applicable or to be relevant, we need to have a system which is isolated. Okay, so what happens is that the internal energy has to be constant. Internal energy is the sum from 1 to n of the occupation of each cell, and let's just call the energy associated with one cell in the mu space, let's call it epsilon I. Okay, so that's the energy of a cell, and the total contribution of a given cell to the total energy will be the number of particles in that cell times the cell energy, and this gives you the total internal energy. So how do you solve an optimization problem with constraints? So one elegant way to do it is a method of Lagrange multipliers, and just remember, so what we want to do is to do differentiation. Here you normally use in calculus of variations, you use this notation, this delta, but of course we use this delta for imperfect differentials like heat, work, and so on. So what we're going to do here is to use some sort of thing like that. In the lecture notes you have a pretty calligraphic D, which I cannot make handwritten here. And okay, so we want to somehow impose extremum condition in the logarithm of the statistical weight, but we have to also obey the constraint. So what you do is you have to here subtract the constraint. The first one, for instance, is that the number of total number of particles is given, and this you accompany by a multiplier. Okay, so let's use the same notation. It's a gamma. And then you also have the constraint on the energy, and here you introduce a second Lagrange multiplier, which tells you that the internal energy has to be given value u, okay, and has to remain constant. And this whole thing, let me just maybe make it a bit smaller like this. This whole thing equals 0. Okay, that's what you do when you apply Lagrange method. So okay, let's differentiate. So just remember what that is, right? That is this thing. So when you make the differential of it like that, logarithm of that this is a constant, so it just goes away, and what you have is the sum I to m of the differential of ni, and here you have logarithm of ni, and then you have a second term which is it's ni. Well, it's not, yes, it's plus because the minus is outside. This ni 1 over ni differential of ni, like that. Okay, so this goes with that, and what you have in the end is let's just write it like this, sum I m, and here you have the d and I, okay, times the logarithm of ni plus 1, which is this one here. And then in the second term here is just directly just the gamma and the differential of ni, which is outside of the parentheses. I don't have to put it. This is a constant, so I don't care. And here I have a similar term. So this would be beta times epsilon I times differential, which is outside. And the internal energy is a constant, so it goes away. This thing has to be equal to 0. Okay? But of course, as usual, this variation, right, it's an arbitrary thing. And this has to be 0 for any variation. The only possibility is that the parenthesis here is equal to 0 always. So what we are saying is that the logarithm of the, if you like, equilibrium occupation, so the occupations that maximize my statistical weight subjected to these two constraints, has to be equal to minus 1 plus gamma minus beta ei. Okay, I'm just setting this parenthesis equal to 0. Now this is annoying. I have 1 plus gamma. That's, I don't want that. I want to have a single constant anyway, right? Because it's an arbitrary multiplier, gamma. So I could call the whole thing alpha. And then I exponentiate this thing. And I say that the equilibrium occupation, equilibrium between inverted commas, so just the occupations that maximize the statistical weight of our macrostate, are going to be e to the minus alpha, e to the minus beta, epsilon I. Okay, that is the equilibrium occupation that maximizes my Boltzmann entropy. So we have to insert that into the expression of Boltzmann's entropy to see what we get out. So remember, there is the Boltzmann constant. Here you have n logarithm of n, that's what we wrote before. And here you have a plus sum from I to m of ni alpha plus beta epsilon I. And this, if you calculate both things there, what you have is k n logarithm of n, and here you have plus alpha and then the sum of ni, which is n, and then you have plus beta and the sum of epsilon I times ni, which is the internal energy, which is here. Okay, so that's u. Okay, and this expression here would be, if you like, the equilibrium Boltzmann entropy. So let's just say equilibrium with inverted commas. SB. Okay, so what comes next is a series of observations about this. So the first thing we're going to do next is to, sorry, this is not probably what I needed to do. We're going to look into this parameter beta. Okay, so we are going to see that this parameter beta indeed is the inverse temperature. Okay, and we are going to see that it makes sense for it to be the temperature, because when you put two systems in equilibrium with one another, this beta of these two systems, when you seek for equilibrium, that is maximization of this guy here in an isolated scenario, these betas of the two subsystems are going to become equal, like the temperature. So it's like thermalization, and this thing, you know, it's going to be positive and so on. So it really makes sense to think about it as a temperature. And we are also going to derive other known results, like for instance the equation of state of this statistical mechanical system. It turns out it's going to be exactly like the ideal gas equation of state. We are also going to derive the Maxwell-Boltzmann distribution, and magically it comes out just like we derived it in the previous lecture. So these things together are going to somehow give us confidence that, at least for this kind of non-interacting gas models, the Boltzmann entropy is indeed the true thermodynamic entropy. So now we are going to see that next.